Hey guys, welcome to Biddy's Math Binder. Before we start, go ahead and take out pencil and paper so that you can follow along with me. So today we are going to look at quadratic transformations. The first thing that we need to understand is the parent function graph. F of x equals x squared. Think of this as the original, it's called the parent function, so the mother. Everything that we do is going to be based off of this graph. So one of the first things we want to make sure we do is look at the pattern that x squared gives us. And if you notice, you start with your vertex at 0, 0. And then from there, you go over 1, up 1. Then you go back to the vertex, you go over 2, up 4. And it's the same on both sides because a parabola is symmetrical. Now, as you look in the table, we can go further. We would go over 3, up 9 if we could fit that on our graph. We could go over 4, up 16 if we could fit that on our graph. And so on and so forth. Every number is just being squared to give us this nice U-shaped parabola. Now you have to know this pattern before you can move any further in today's lesson. If you need to pause this, take a look at it some more, then do so. Now, I want to look at vertex form of a quadratic equation. Vertex form is a times x minus h squared plus k. A tells us some things, and let's look at what those things are. First of all, if a is negative, that means that you're going to have a reflection over the x-axis. So your parabola is actually going to flip upside down to where you have now a maximum instead of a minimum. If a is in between the numbers 0 and 1, then you have a vertical compression, or another way to say that is a vertical shrink. Now that negative only tells you about the reflection. So we don't look at the negative anywhere past that. Now I'm just looking at the number. So if it's in between 0 and 1, that's a vertical compression. Basically a fraction, right? And if a is larger than 1, we have a vertical stretch. Now h is going to tell us some things as well. If we have a plus h on the inside of those parentheses like so, that means that we're moving left h units. And if it's minus h, we're moving right h units. And then the k all the way on the outside there, if it's positive, then we're moving up k units. And if it's negative, we're moving down k units. Now, all of this information is very important for being able to graph a parabola without your calculator. If it's in this vertex form you see here in purple, it's going to be really quick, simple, and easy to graph. Let's look at our first example. You'll notice really dull there, you can see the original parent function graph. Let's see how it changes. First of all, I know that normally the vertex is located at 0, 0. I can see because of the minus 1 on the inside, that means that I'm moving right 1 because it's opposite of what you would think. You see a minus, you think left, so it really means right. Kind of confusing, but you'll get the hang of it. So I'm going to move that vertex to the right 1. My new vertex is at 1, 0. From there, I'm going to repeat the pattern we learned earlier. Over 1, up 1. Over 2, up 4. And then, of course, we're going to repeat that pattern to the left because parabolas are symmetrical. Now we can connect our dots, and we now have a new parabola that has moved to the right 1 unit on all points. Let's look at our next example. Again, you can see very, very dull there in the background. We have our original parent function graph of x squared, and it has a vertex on 0, 0. Now, I have a plus 2 on the inside of my parentheses, so that's going to mean I'm moving left 2. My new vertex is now at -2, 0. From there, I'm going to use the pattern. Over 1, up 1, over 2, up 4, and repeating it back on the left there because parabolas are symmetrical. Now I have a parabola that has moved to the left 2 units. Now this example, I've added a little something to it, made it look a little different. Let's take a look. First, I have a negative in the front. That means I have a reflection over the x-axis. Then I have a +3 on the end, not in parentheses. That means it's going to move up 3. All right, so let's think about this for a second. My vertex is at 0, 0. I know it needs to move up 3, so let's go ahead and do that. Now I'm going to have a reflection over the x-axis. That means that instead of a minimum, I have a maximum. So my graph is going to be pointed downward. So instead of doing the pattern that we know and moving up every time, we need to move down every time. So this time I'm going to go over 1, down 1, over 2, down 4. And then I'm going to do the same thing on the left-hand side and connect my dots. I now have a parabola that not only moved up 3, but also shows a reflection over the x-axis. This next example, we see a 2 in the very front. Well, that's where A is located. 2 is greater than 1, so that means I have a vertical stretch of 2. Now we see that our vertex, obviously for the original, is at 0. I did not move to the left or to the right at all. I didn't move up or down at all. So my vertex stays at 0, 0. Now here's the tricky part. Because I have a vertical stretch of 2, every point that I move vertically needs to be multiplied by that 2. So normally we move over 1, up 1 as our first step. But instead of moving up 1, I want to multiply that by 2 to get my stretch. So really I'm going to move over 1, up 2. Next, typically we move over 2, up 4. So this time we're going to move over 2, up 8. And that goes off the page, that's fine. We're going to do the same thing to the left. And we get this parabola that looks skinnier or more narrow, which makes sense because we have a vertical stretch, and that's what's always going to happen. Our graph is going to get a little thinner. Let's look at this next example. First of all, the original always has a vertex starting at 0, 0. We know that. That 1/2 in the front, that means vertical compression of 1/2. You could also say vertical shrink if you wanted. They mean the same thing. And then that -4 means down 4. So, okay, I'm going to move my point down 4 to have my new vertex at 0, -4. At this point, I need to apply that vertical compression. So again, every point vertically needs to be multiplied by 1/2. So normally we move over 1, up 1, but 1 times a half is a half. So we need to move over 1, up a half. Normally we do over 2, up 4, but half of 4 is 2. So over 2, up 2. Next, I still have room. Let's go over 3. If we think about the original graph, if we moved over 3, then our pattern tells us we would go up 9. Well, half of 9 is 4.5. So I'm going to move over 3, up 4.5 units. If I want to continue to go, I can move over 4. My original pattern would mean over 4, up 16. Okay, so half of 16 is 8. So over 4, up 8 units. At this point, that's going to be as much as I can fit on this graph. So now I can move to the left and repeat all of my points because, of course, parabolas are symmetrical, so they all need to go onto the left side as well. Now I can connect. There is my new parabola that has a vertical compression of 1/2, but also moved down 4 units. We're going to do one last example. We can see our parent function graph there, which of course has a vertex at 0, 0. If I look at my function up top, I see a negative in front. That tells me reflection over the x-axis. I see a -2 on the inside. That tells me right 2. Then I see a +5 all the way on the outside. That tells me up 5. So, okay, let's think about this. My vertex at 0, 0 needs to be moved to the right 2 and also up 5. Now that I have that, I have to remember I'm going to reflect over the x-axis. So instead of moving up every time, I need to move down every time. There's no vertical stretch or vertical compression, so I don't have to worry about multiplying my original pattern by anything. I can just use it. So over 1, down 1. Over 2, down 4. Over 3, down 9. And again, I'm going to repeat that same pattern to the left to get the other half of my parabola. That is my final answer. All right, guys, that's the lesson for today. Be sure to subscribe for more math videos.